Chapter 10, Section 2, Problem 19. Problem 19 is one of these that builds across the chapter. So in Section 2, Problem 19 is the foundation for what's going to be in Section 4, Problem 19, and also in Section 4, not Section 4, but Section 5 or Section 6 or Section 7. So Problem 19 is the same foundational problem across this whole chapter. Let's look at it here. So number 19, 50 male subjects drank a measured amount X in ounces of a medication and the concentration Y in percent in their blood of the active ingredient was measured 30 minutes later. The sample data are summarized by the following information. And this is looking suspiciously like what we need to do for the sum of squares stuff. Okay, compute the linear correlation coefficient for the sample data and interpret its meaning in the context of the problem. So again, we've got the linear correlation coefficient, R, is what we're going to be looking at, and then we have to interpret what that means. So again, we have this point that we have minus 1 is less than or equal to R is less than or equal to 1. So if R is near either one of those ends, there's a lot of correlation. If R is near 0, then not much correlation. All right, since we have the data here, and we just did everything in Excel in Chapter 10, Section 2, Number 11, I'm going to use that same structure and do an Excel sheet for this problem as well, kind of copy that over. So if you've watched Number 11, you'll see what's going on. If you haven't, that's where you'll see the details of what's happening here in Number 19. I'll go fast through it here. I went through it in more depth in Number 11. All right, so here we are, 219. What I've essentially done is come through and taken the data here, that was the data in the problem, and spelled it out. And as I look at it, let's see what we have here. I took that value that 0 is less than or equal to x is less than or equal to 4.5, toss that in here. It's not something we're using right now. We'll be using that later. So we were given the sum of the x's, and we were given the sum of the y's. So we were given the sum of the x squareds, so that's each individual x squared added to another individual x squared. And we were given the sum of the y squareds, so each y squared added to the next y squared and summed all up. We're also given the sum of the xy's, so x times y plus the next x times y plus the next x times y summed up. Now we can actually calculate from this the sum of the x squared, because we were given the sum of the x above, so we square that. So essentially here what I'm showing is it's d7, that caret 2 or hat 2 is to be squared, d7 squared, gets us the value we need for the sum of the x squared. Then we have the sum of the y squared, same thing but with y. And we were given n, which was the number of observations that we have, or data points. Now essentially what I did here, if you were looking at the screen, you can see down here at the bottom I've got stuff going on that essentially took the problem we had on number 11 and I just copied it over to another tab, so I had it structured. So I had the formulas already in place. So my formula for the sum of the squared of x's is the same formula I had in 211, because I had everything here in the same spots up above in terms of where I had my values. So it's the same formula, which is the formula right out of the book put into Excel form. Same for the sum of the square of y's, and same for the sum of the square of the xy's. And then because I had the sum of the squares all in the same relative location to the linear correlation coefficient equation, my equation for R is essentially already done for me, because I did it for problem number 11. So you can see here it's that R is the sum of the square of the xy's, so D18, sum of the square of the xy's in blue, divided by the square root of the product of the sum of the square of the x's times the sum of the square of the y's. So the sum of the square of the x's was the red, sum of the square of the y's was the purple, and they were already there in that same location that I had them back when I did problem number 11. And there we go. That gets me the correlation coefficient quickly. As I mentioned in the other video, got lots of values here of significant digits. Don't need all those significant digits. So in this case, my linear correlation coefficient for problem 19, R, is 0.965. And as I was just mentioning back here on the other page, 0.965, so R equaling 0.965 is close to 1, so it's relatively close to 1, which indicates there is a lot of correlation between the amount that the medication that was drunk in ounces is strongly correlated to the concentration Y in the blood 30 minutes later of that active ingredient. Interesting. So there, much faster because we used that same sheet. Now, you may ask, okay, I see you're using Excel. You're welcome to use Excel, as I did here in this example and the example in number 11. And encourage you to, if you're doing that though, spell out all the values of some of the x's, some of the y's, some of the x squared. You can use a notation like I did here for what that means and how those numbers are derived. But do it from either the standpoint and actually use the equations to show what's going on. If you're given data, you can see these, there's no equation in those. However, when I get down to some of the x squareds, like we mentioned before, there's the equation that we went through a little bit ago for that. So Excel is a fine tool. Make sure that you include the actual Excel sheet with your homework when you're submitting that so we know what you've got there. All right, great. There you go, number 19.